All right. So the next speaker is Hayato Kanno. He'll tell us about Grassman Tensor Renormalization Group for two-flavor massive Schwinger model with a theta term.
Thank you for introduction and thank you for giving me this opportunity. I'm Hayato Kanno from Riken Research Center, but I just arrived here for 2 weeks ago, so this is really my first time to visit to the US. Yeah, and I will talk about this title. And this work is based on the ongoing work with Japanese lattice QCD people. So, okay, shall we start? First, I will summarize my talk. So, in my talk, I will talk about the result of the numerical calculation of the two-flavor Schwinger model by a kind of tensor network method, and I focus on the numerical calculation of the free energy, in particular theta dependence of the free energy. Okay. This is the introduction slide, and the main motivation is the numerical calculation for the finite theta QFT with the finite theta parameter. So it is well known that if theory includes a theta term, this is a topological term, as you may know, and if theory includes this term, the Monte Carlo simulation does not work well because Monte Carlo simulation using this Boltzmann factor as a weight of the how to say sorry using this Boltzmann factor in principle, if this Boltzmann factor is real valued, this Monte Carlo calculation works well, but if it includes imaginary part, it is difficult to calculate. So there are some previous studies, but theta equal to, in particular, large theta part is very hard to calculate. However, currently many kinds of tensor network methods are developed. So this is a good tool to attack some QFT with such sign problem in the lattice QCD context. But tensor network methods are developed in the condensed matter field. So it is some of them are very difficult to apply directly for the QCD or large system, but it is good to work in 2D or 3D or some low dimensional theories. So in this talk, I will focus on the Schwinger model. This is 2D QED. Yeah. And there's some previous studies in the Hamilton formalism, including works of the Princeton people, but I will use the tensor network method by the Lagrangian formalism. So I will use a different method to calculate this model. Okay, this is my talk plan, and okay, I introduce the Schwinger model, but this is well, maybe you may know because Ross introduced this action in before the lunch. So I calculate this model in the two-flavor case, and this Schwinger model is well known as a toy model for the QCD because after bosonized this theory is equal to the pion theory plus eta prime meson. This is very similar to the 4D QCD. Yeah, and if massless case, this theory, it is known that this theory goes to the SUN level 1 Witten CFT fixed point. But so there is a gapless point. And it is also known the first order phase transition point at theta equal to pi point. So I will check these in the numerical. So in our work, we focus on the theta dependence of the free energy, and some of four various mass parameters, and we separate these four regions. The mass we separate these mass parameters for these 4 regions. And number one, the massive limit is known as just the Yuan Maxwell theory, and the theta dependence of free energy is well known. We can calculate it by hand. And also, massless region, so small mass region is also calculable. This is calculated by this Coleman's famous paper, and free energy proportional to some power of cosine. And these factors are well defined, so I mean that there is no ambiguity for these factors. So it is very good to cross-check between the theoretical value and numerical value. Okay, and intermediate mass region, there is no knowledge by the analytic way, so we need to calculate numerically here. And I will comment the massless part because there is no theta dependence in the continuum theory. So next I will explain my numerical method. My numerical method is a tensor renormalization group, and this is just a real space renormalization for the tensor network. So I calculate the Euclidean spacetime, and partition functions can be rewritten for the tensor network. And after rewrite this partition function as a tensor network, we just focus on this tensor. And renormalization step is written as here. So first, this tensor, we get this one tensor, and we decompose this tensor for 2 3-leg tensors and just contract the original legs, and then we can get larger lattice, and we continue this process again and again. And so this is our numerical method. One strong point is we can directly use Grassman degrees of freedom, so we can direct to calculate the fermion. And it is also possible to calculate the large volume limit. And this is a lattice action, so we use 2D staggered fermion. So this is correspond to the 2D Dirac fermion in the continuum theory. And we need to discretize this U1 gauge field for the some finitely many points. And in our calculation, we use these parameters. Okay, I will show you the numerical result. And what we calculated was this theta dependence of the free energy. And we plot the free energy as a function of theta, and it is very clear to this figure has a 2 pi periodicity for theta parameter. And we can also calculate the ground state degeneracy in our method because of the this ratio of these contraction tensors correspond to the ground state degeneracy. And in this figure, this right-hand side is a large volume limit, so this is we want to focus. And only theta equal to pi point shows the 2 vacuum degeneracy, and the other points, even if slightly different from the theta equal to pi point, shows 1 vacuum. So this is a very interesting result for ours. Yeah. And next we check the some mass regions. In the large mass limit is well known the analytic continuum result, and our result overlap with this analytic one. But small mass limit in the massless point, the free energy should not depend on the theta parameter, but we found that this goal plot, so our numerical result depends on the theta. This theta dependence disappears in the large beta limit. This is the continuum limit, so this is a lattice artifact in our setup. So our result in the small mass regions are affected by this lattice artifact gold plot, so this is very far from the continuum result. So we just subtract this lattice artifact from the small mass result, and we plot it again, the difference from the lattice artifact and small mass region. But we could not realize this, our numerical result overlap with the continuum one. So this is the problem now currently we have. And finally, we can also calculate the finite mass parameters, and we check the smoothly change the theta free energy of the theta parameters for the mass several mass parameters. Yeah, this is the conclusion. We calculated the two flavor Schwinger model by the tensor network tensor renormalization group method, and we calculate theta dependence of the free energy. And we check the consistency in the large mass, and the consistency in small mass is very weak, so we need to consider how to calculate the small mass region. So that's all. Thank you.
Yes.
On your degeneracy plot, you had points that were not integer. What did I misunderstand? What's that's telling me?
Sorry, this degeneration means the value of this this value. I plot this value, and if in this region, I think it is not good to understand as background state degeneracy, because we could not take the large volume limit, so we could not. In this region, the non-integer value is has not any meaning, and the meaningful one is these are large volume limit results. I think, yeah.
So a very, very naive question. I'm going to say something wrong, but I'm not sure what. So if I wanted, I could add like cosmological constant, right, to the model. Something depends on theta.
Yeah.
So I could change the free energy, right? Like the free energy doesn't seem universal, right? Like I can change it by adding cosmological constant, right?
What? I'm sorry, I don't.
You just add a constant term to the Lagrangian that depends on theta, right? That shifts the free energy, right?
Yeah, right. Which depends on if it depends on theta. Yeah, theta will be changed, but I mean.
So this doesn't seem universal, right? Because I can change it if I want.
I'm sorry. I just checked the difference between theta equal to 0 point and theta equal to non-zero point. So I normalized this partition function value of partition function at the theta equal to 0 point, and I did not add any additional term than this Schwinger model. So this
gets
has
rid of
no
a term that does not depend on theta, right? If I add a constant, that difference eliminates that constant. But if I add a constant that depends on theta, like cosine theta.
You define the derivative with respect to theta as an insertion of FF dual. Well, an insertion of F here. So I mean that's a definition.
F can mix with the unit operator. F can mix with unit operator. There's different parity. That's only theta equals 0. You cannot do that otherwise. So the UV finite C should be.
I mean, that means that the counter term is finite, but not that it's necessarily 0, right?
I'm sorry.
So the fact that the theory is finite means that the counter term is finite, but it doesn't mean that it's literally 0.
There is no counter.
Yeah.
Anyway, it's a
I'm sorry.
doesn't matter.
Any other?
So in Coleman's paper, when he discussed theta equal pi, did he know that even at large mass there would be this double degeneracy at theta equal pi? I forget.
In Coleman's paper, nothing written for the large mass region, but
But he thought that in large mass region, I thought.
yeah. He wrote something about large mass.
Didn't he discussed how to mesh together the large mass and small mass regions? But my impression was that he maybe did not think that the large mass region would have double degeneracy. But
But I think at least the large mass limit, Maxwell theory has a two bucket degeneration it is well known, I think. So to naively extrapolate from the massive limits from the Maxwell theory to the finite mass, so this theory should have the two vacuum degeneration. Theta equal, even for theta equal.
Okay, let's thank Hayato again.